Thank you, Martina, for the introduction. Good morning, everyone. It's a great pleasure to be with you this morning. It's a great pleasure to be in the virtual Basque country. Thanks for, also I would like to thank the organizer for putting together this very nice event at the boundary between quantum optics and maybe more quantum material topics. So today I will speak about Josephson metamaterial, sorry, and I will present you a series of recent experiments we've done thanks to this Josephson metamaterial. So I put it, I put a picture here. I guess you all see my mouse, and this is what I call a Josephson metamaterial. In this case, this is a 1D array, a chain, if you want, of Josephson junctions. You can have large ones here, smaller ones in red. So you have any, experimentally, you can build any type, any combination of small, large, medium-sized Josephson junction, and I will explain you now what's fun with that. But before we start, I would like to thanks and acknowledge the hard work of all the people directly involved in this work. More specifically, Luca, Arpit, Anuj, and Martina, who are really the driving forces of the experiment I'm gonna present today. But of course, I also would like to thank the whole superconducting quantum circuits team in Grenoble. And also, we have various collaborators around the world. Thanks to them as well. So today I wanted to start with this picture. It's not from me. I guess most of you have seen it in the past. It's taken from this very famous paper. I would call this paper probably the seminal paper of circuit quantum electrodynamics. It's a theory paper by Alexandre Blais, and basically it was the first time, or almost the first time, that people were somehow to bridge the physics of superconducting circuits and the physics of quantum optics. And basically in this nice paper, they explain us that if you would couple superconducting qubits, this green device here, to a resonator, a micro resonator, this is the blue strip here, you could basically do a lot of very nice and deep science experiments, and basically study light matter interaction on chip. So obviously I've been working in this field for many years, so I'm not very much objective, but I think this was really a great idea, and it opened many perspectives. So putting a qubit in a resonator, no doubt it was very powerful idea. But still today, I would like to ask a very simple question, and this question is there an advantage to get rid of a resonator? So can we live without the resonator? And more importantly, is there any advantage? Because you can always say, oh, look, for, I don't know, fundamental reasons, I want to get rid of my resonator, and then I will somehow downgrade my experiment. And but since it's new, it might be interesting. No, this is not really that. I want to really, my question is there any advantage, and can we do better without the resonator? And of course, the answer is yes, because if it would be no, probably I would not be speaking in front of you this morning. So, and the key point is that if you want to get rid of your resonator, you need to somehow engineer a bit better the material of your experiment, basically the metamaterial of your experiment, because if a resonator is used to enhance light matter interaction, so now you need to work back, to work in a different direction to increase again this light matter interaction, and this is basically what I'm gonna tell you today. And of course, there are many applications. I had to choose one, and the use case basically I'm gonna discuss today is ultra low noise amplification. So first, let me tell you what I mean by amplification. So in many cases, you have a quantum system and you want to measure it. So what you do is that you send a probe in, this probe reflects on your system of interest, and then you want to measure the outcoming probe, measure its phase, measure its amplitude, measure its number of photons, and no matter what you measure, you want to acquire information about your quantum system. The catch here is that we are dealing with very low energies because it's a quantum system, so we speak about a signal on the order of few photons. And of course, if as an experimentalist, you want to measure this signal, you need to amplify it because you cannot measure nanovolts or microvolts with a standard oscilloscope. So you need amplification, right, to just make your signal larger. But also you need low noise because, if you amplify your signal, but you add a larger noise than what you get when you win with the amplification process, basically you actually lose everything. You want to optimize the signal to noise ratio. This is something I will come back to later on. So these are the two key points. So now let me tell you a bit more. Why is it interesting? Maybe let me give you some perspectives. So obviously, the quantum system you might want to measure are qubits. These are the first applications that come to mind. They could be superconducting qubits or spin qubits, and in both cases, you want a very good low noise amplifier. What you might be less familiar with is the bottom row here, because there are other applications to very low noise, ultra low noise amplifiers. One of them that I like very much is dark matter detection. Our high energy colleagues, high energy physicist colleagues, they told us that, okay, there might be some dark matter in the universe, and it's a somehow a missing block of our understanding of universe, and we need to detect it. It's obvious, it's going to be a very small signal. So if you can get a very low noise amplifier, you will have a better signal to noise ratio, you will measure faster, and eventually you might be able to detect this dark matter. There are also a strong interest in the frame of quantum limited ESR, which means electron spin resonance. So basically, if you want to detect a small ensemble or even a single spin, you need extremely low noise amplification. If not, you will not be able to detect your tiny spins. And last but not least, our astrophysicist colleagues, they are now building crazy detectors. We speak about actually not even a detector, it's a camera. It's really a camera with many pixels. So this is what you see here. All these little dots there are actually pixels that astrophysicists use to detect, basically they point their telescope, they point their camera to the stars and just observe what's going on there. And again, if you can get a very low noise amplifier, an ultra low noise amplifier, they're super happy because they can, scan faster, detect smaller signals. So this is just, these are not all the potential application. Of course, I had to select only some of them, but I think it gives you a kind of nice overview of what's going on here. All right, so now let me introduce a couple of basic concepts. And for that, I like very much this sentence from Carlton Caves. It states that the last essential quantum mechanical stage of a measuring apparatus is a high gain amplifier. It produces an output that we can lay our grubby classical hands on. So this is basically what I told you before. If you want to be able to measure your signal, you need basically to amplify it. But you need to amplify it in a quantum mechanical way. And this is the key point. And in this seminal paper from Caves, of course, he explained us why do you need an amplifier. But very importantly, I think he was the first to derive what is called today the standard quantum limit, which states that no matter how hard you work, no matter how smart you are, the noise added by your amplifier will be at least h bar omega divided by 2 kV. This is the so-called standard quantum limit. And so knowing this, Now you might want to put such a quantum limited amplifier in your setup. And this is a typical setup in our lab. This is a dilution refrigerator. So basically you have various stages at various temperatures. Of course, your qubit or your fancy quantum system sits at the coldest stage. And then you want to amplify it, if possible, with a quantum limited amplifier. This is our first amplifier. And then you usually need a second amplifier, and sometimes even a third amplifier to make your signal bigger and bigger and bigger. But if your first amplifier is extremely good, if it's quantum limited, I will show you now that if the second one is not as good, it's still fine. And a way to understand that is to work out a very simple calculation of cascaded amplifiers. So you have an input signal, an input noise, first amplifier, second amplifier. Both of them, they add their own noise. So this is the noise added by the first amplifier. This is the noise added by the second amplifier. And what you can show in a couple of lines of calculation is that the total noise, what we call the system noise, so really the noise of the full measurement chain, is the noise of the first amplifier plus the noise of the second amplifier divided by the gain of the first guy here. So basically, if you can make the gain of the first amplifier large enough, you will be able to overcome the noise of the second amplifier right here, and the system noise, your measurement chain noise, will be quantum limited. So this is basically what I depicted here on this graph. This is the system noise temperature in unit of TSQL versus the gain of the first amplifier. And what you see is that as soon as you increase the gain of the first amplifier enough, that means above 20 dB, then basically the whole system noise is again quantum limited, even though the second amplifier is not quantum limited. So basically you can summarize this kind of graph in two conditions for your first amplifier. First, obviously, it should be quantum limited. And second, it should display again large enough so it overcomes, the noise of the first amplifier overcomes the noise of the second amplifier. So this is our wish list for today, and I will come back to that later. All right, so now how do you go there? Because Caves told us that, okay, there is a quantum limit, but it didn't give the recipe, right? This is sometimes the problem with our theory friends. So basically, we use parametric amplifiers because they can reach the quantum limit. I don't have time to somehow demonstrate that. I will just ask you to trust me on that. But basically, parametric amplifiers, since they have a very well-controlled number of modes, they are able to reach the quantum limit. So you probably all know the parametric oscillator. This is the case of the swing. So basically, a swing is a parametric oscillator that you might actually see also as a parametric amplifier. Of course, we don't work with a swing. We work with circuits, and more specifically, as I said, with Josephson junction. And a Josephson junction can be seen as a variable inductor. So basically, if you pump your system at the right frequency with the right amplitude, you can get parametric processes, you can get parametric oscillations, parametric amplification. So to make a long story short, a parametric amplifier is an amplifier with which you get amplification via the periodic modulation of a parameter. It can be the moment of inertia in the case of the swing, or the impedance of the case of a circuit. It can be, I don't know, you have other physical systems. So any parameter that you might modulate at the right frequency with the right amplitude might be able to offer you a nice parametric amplifier. So now, if I jump to the quantum version of what I just explained, so it's just a quantum optics point of view. This is the picture we have. So it's what I'm going to say now is exactly similar to the classical picture I gave before, just that now I'm going to speak about photons and processes, microscopic processes, but basically whatever the picture you choose, they should give you the same answer except if you are interested in noise, of course, but this is not exactly what I'm going to discuss today. So let's jump to the quantum optics picture. So you might see your amplifier as a nonlinear material, and you might want to represent this nonlinear material by 3 levels. Of course, this is a cartoon, but I think it's quite interesting to understand the physics this way. So if you pump your material, basically you will excite with 2 photons, you will excite it up to this second level here. And if you have an input signal photon, because of stimulated emission, your medium will de-excite and you will generate 2 signal photons and 1 idler photon at the same time. This idler photon here is just here because basically you need to fulfill energy conservation. There is no magic here. If you have 2 pump photons and 1 signal photon, basically you need an idler photon, a complement photon, to make sure that you fulfill energy conservation. This process is called 4-wave mixing in quantum optics. And if you look at the net balance between input and output, basically you see that here you have 1 signal photon, at the output you have 2 signal photons, so basically you have a gain 2 amplifier. Of course, a gain 2 amplifier is nowhere close to the 20 dB wish list I told you before. So 20 dB for a non-experimentalist, I would say, is 100. So we are very far from 100. So to get to the 100 gain, what we can do is to put our medium into a cavity. And if you put your medium into a cavity, you might then define an interaction time, which is basically the cavity quality factor, divided by the cavity bandwidth. And if you have an interaction time which is long compared to the escape time of your cavity, then you might get some larger gain than 2. So we start with our input photon. We have a first parametric process. We get 2 photons, that we get 4, and then you can play the game again and again up to get, up to gains on the order of 100. Of course, this is a cartoon picture. Life is a bit more complicated, but this is really the idea. If you have an interaction time which is long enough, you can get a gain which is large enough. Of course, here there is a price to pay because you will have a limited bandwidth. You have a cavity, so you have a narrow band. So there is another way to get parametric amplification. And this is what I'm going to discuss today, and it's called traveling wave parametric amplification. In this case, you have a distributed medium, a dissipationless, if possible, nonlinear medium. And in this case, the interaction time is basically the medium length divided by the wave velocity. So you don't have any more cavity, you're cavity free, and your interaction time is just long enough if you have a medium which is long enough. This is why basically you need the material. You need to really engineer cell by cell your nonlinear medium. So basically at the end of your device, which is here, you have a gain which is large enough. So here I represented the 3 waves I mentioned before: the pump wave, the one which gives energy, and then you have the signal wave and the idler wave, and you see that at the input you have a very small signal and idler, and at the output you have a large signal and idler, and then you can calculate the gain of your amplifier by calculating the ratio between output and input, and you see that you can get quite large gains in this case. This is so this traveling wave parametric amplification is well known. It's been used in optics for, I would say, decades. In this case, the material are usually, basically they use crystals, nonlinear crystals. In this case, if you want to be a bit more formal, you might want to write the polarization versus the electric field propagating. So the electric field is a propagating field. So if you write a polarization versus propagating electric field, you see that you have the first linear answer. So polarization is just proportional to electric field, but you have also nonlinear polarization, chi2, so second order polarization, or third order, and chi3, which is the third order response function. So this chi2 and chi3 are basically the nonlinear response function. And basically, this is how we describe amplification in this case. In circuit, we can follow somehow similar approach, and we just replace the crystal, the real material, by a metamaterial, which is just, as I said, an array of Josephson junction. And in a very similar way, we can pump this metamaterial and input a signal as well. And at the output, we have a pump, which has been, somehow, which has given some energy to signal and idler. And in this case, the two relevant parameters are not anymore polarization and electric field. It's more the phase. The phase is nothing but the integral of the voltage. And it's also a propagating phase and the current. So phase is the equivalent of the electric field in our case, and current is basically the equivalent of the polarization. But now, since this metamaterial is made of, oh, Martina, it means I already have, it's only 5 minutes left. Okay, I have to speed up then. So basically, we have a nonlinear metamaterial. So basically, we also can have a chi2 and a chi3 interaction. So this is following this idea, we decided to build such a metamaterial. So you see here, we have an array of Josephson junction. And if we measure the gain of such an amplifier, this is the kind of curve we obtain. So basically, you see a nice gain profile in the case of the traveling wave amplifier. And you see also a nice gain profile for the resonant amplifier case, but you see it's much narrow band. So I think this figure illustrates quite nicely the advantage of getting rid of a cavity. You see that the bandwidth is decades order of magnitude larger in the case of the traveling wave amplifier. But still, there is a flaw here. There is a little issue because, as I told you, we want a 20 dB gain. The problem is that, you see, we reach this 20 dB gain easily with the resonant amplifier, but we are very far from 20 dB in the case of the traveling wave amplifier. And this is really a problem. And now there is some physics to understand. And it's the following one. As I told you, we need to fulfill energy conservation. But since now we are dealing with propagating waves, we also need to fulfill momentum conservation. So momentum conservation is just that. So you have what we call the phase matching, the total phase matching, which is 2kp minus ks minus ki. And you want to make this equal to 0, because if you don't fulfill momentum conservation, basically, you get a lower gain. And this is why we get only 10 dB of gain. So I will probably go a bit fast here, since my timing is running. So this phase mismatch can be decomposed in two parts, delta k naught and delta k care because it's the care effect, it's a non-linear effect. So basically, you have a phase mismatch which comes from the linear part of your wave equation, which is this one, and you have a non-linear phase mismatch which is caused by the non-linearity itself. The fact that you have a non-linear medium, the fact that you built an amplifier on purpose, causes you trouble as well. So basically, you have to somehow engineer your device so that you can make this delta k as small as possible, because as you might see here, the gain is maximal when delta k is equal to 0. So there are many ways to solve this phase matching problem. In optics, they came with many solutions. We have something more in our hands because we have the ability to tailor the metamaterial, the material cell by cell. So this is really something we wanted to play with. So basically, this is how we solved the phase matching problem. We did some dispersion engineering. So instead of having a homogeneous array, we somehow modulated the size of the Josephson junction. So basically, if you want, the impedance is modulated the impedance of the device is modulated versus length. So and this is well known in solid state physics. This is well known in quantum optics. If you have a periodic modulation, a special periodic modulation of your device, you will open a gap. This is called the Bloch theorem. It's nothing new, it's all physics, but you will open a gap in your dispersion relation. So if you plot wave vector versus frequency, you open a gap in the dispersion relation, and basically close to this gap, the linear phase mismatch becomes negative. So basically, you have a negative number here, a positive number there, and you might then you might make the total delta K equal to 0. So if you play this trick, this is the kind of gain plot you obtain. So this is called, we call that a podium plot. This was made by my student Luca. We found it nice. So basically, it compares the resonant amplifier to the bare traveling wave amplifier to the band engineer traveling wave parametric amplifier. And you see that with the blue curve, now we have everything we need. We have a large gain and we have a very broad bandwidth. Since I have a little bit of time left, I also want to show you that we can do even better. So basically, what's cool with multi-material is that you can engineer everything. So before I told you that we might want to do some linear band engineering and adjust this delta K naught, the linear part of the phase mismatch. In a very recent work, we were able to engineer the nonlinearity itself. So what we did was to replace a standard squid by an asymmetric one. We call it SNAIL in our jargon. It stands for superconducting nonlinear asymmetric inductive element. And in this case, what you can show is that you can reverse the sign of the nonlinearity. And if you do so, basically, you can make this part negative. So you have a negative phase mismatch because of the nonlinearity. Of course, here you don't do anything. You don't do any band engineering on the linear part. So this one remains positive. But since now this one is negative, you have a delta K, which is equal to 0. So this is these are various cartoons, various pictures of the device. But let me jump directly to the results. So basically, this is the 2021 curve, the green curve, which is the latest device in our portfolio, I would say. It's a reversed care traveling wave parametric amplifier. And you see that now by engineering the device at the nonlinearity level, we could get even more gain and even larger bandwidth. So basically, I think this graph illustrates quite nicely what you can gain, what you can win whenever you transition from a resonant amplifier to a traveling wave parametric amplifier. So I think it's now time for me to conclude. So these are the various papers which describe this work. But maybe if I have one more minute, I would like to speak about perspectives because it's usually a bit more interesting. So we are now working hard in the direction of microwave quantum optics. Since we understood quite well what's going on for amplification, now we really want to look at the statistics of the photons, and these are preliminary results we obtained very recently. Basically, we could generate a multimode squeezing, broadband multimode squeezing in such a device and demonstrate quantum entanglements. Fortunately, I don't have time to tell you about that today. Also, and I think this is really very relevant for this conference, we still would like to engineer the next generation traveling wave parametric amplifier. And I think yesterday there was a very nice session about non-reciprocal devices. So the question is, can we make these broadband traveling wave amplifiers non-reciprocal? And I think we might hear about that in the two coming talks. Okay, and then I also wanted to make a little bit of advertisement. So if you're not too much afraid of snow, and if you like mountain, and if you want to have fun with us with these devices, maybe you want to join the team, since we have postdoc and PhD position available. And with this, I will conclude, and thank you for your attention.
Thank you very much, Nico, for the very nice talk. So the stage is open for questions. So we have time for a couple of questions. So I encourage the attendees to raise their hands virtually so we can unmute them or to type the questions in the chat. So we have one question in the chat from Anya Mettelman. Great talk. How are the noise characteristics for the TUPA with and without dispersion engineering?
Okay, Thanks. So I will answer in 2 steps. So in principle, it should be the same. So as soon as you have only the parametric process that you want, in this case, the 4-wave mixing parametric process I discussed, the dispersion engineering should not impact your noise properties. So in other words, whether you have or not band engineering, your 2-pa should be quantum limited. That's the first part of the answer. Of course, life is not as easy. And what happens in any parametric device is that usually you have other processes. So you might have 3-wave mixing, you might have frequency doubling, you might have frequency sum. And these other processes, they might combine with your the process you want, and this will degrade the noise properties of your amplifier. So to answer your question more precisely, with band engineering, you might be able, or dispersion engineering, you might be able to kill these unwanted processes, and you might be able to get better noise performances.
Great. Thanks, Nico. I'm afraid we have to move on, but I encourage the attendees to type their questions on the chat, and Nico, maybe you can answer later on the chat. Thanks again for your talk. So we can move to the next talk of the session. We have Vittorio Piano. Vittorio, you can share your screen, great. From the Max Planck Institute in Erlangen, Germany. So Vittorio, the stage is yours.
Can you hear me? Okay, great. Okay, so first of all, thank you very much for the organizer for putting together such a nice and interesting talk, and also for inviting me. So today I'm going to talk about a proposal. So the organizer, they even asked me to talk about this proposal that we put forward in 2016 about a topological traveling wave amplifier. So it's very much related to the talk you have just read, and this work you have just heard about, and from Nicola. And this work was in collaboration with the group of Ashclerk, back then in McGill, now at the University of Chicago. And I want to start the talk with a very bold claim that our work was of some historical significance. And for this, I will have a 1-slide history of topological photonics. And of course, it all started, as you all know, with the discovery of the quantum Hall effect. And so that in general, there are topological band structure, and in presence of topological band structure, you can have robust transport. And only after more than 20 years, Haldane, for the first time, pointed out that this is actually a very general wave phenomenon, and that it applies also to classical waves, and in particular to photons. And then for the next decades, I would say, the challenge that the pioneers of topological photonics had to face was to translate these ideas from electronics into the realm of photonics, and so to find suitable setups. And so for this reason, for a long time, most of the work had 3 features in common. So it was a lot focused on proof of principle experiment. And then the photons were mimicking a well-known physics from an electronic analog. And also quantum mechanics did not play any role, because photons are wave in the classical realm. And in 2016, we put forward our work that somehow breaks all these 3 paradigms. And of course, here I don't claim any causality, but this was at the beginning of a very exciting era we went to, where people are investigating active topological devices, also looking in quantum feature of these devices. Okay, so here also I have to thanks, Nicola, for doing some nice job about talking about quantum limited amplification. So yeah, the idea is that we also want to have a quantum limited amplifier, and we also have our own wish list. So mainly there are two features already highlighted by Nicola. So we want to have a broadband amplifier, so there should be no trade-off between gain and bandwidth. It should be quantum limited. So in theory, this means no information should be disseminated in the environment. And here we add another element to the wish list. So we want it to be fully non-reciprocal. So if you inject something in the output port, nothing should arrive into the fragile quantum system. And this is where the topology of our system will come to rescue. Okay, and then here in what is the idea in a sketch? So we just combine two ingredients: this topological band structure and parametric driving. Okay, and yeah, so I will try to summarize the whole work in 2 slides and then go back to it and tell you more details on this. So basically what we are doing is combining in a clever way a system where we have an array of cavity that can where the photon can hop from cavity to cavity, and if they go around the plaquette, they pick up a phase. This is what is known as a synthetic gauge field, and we combine this with parametric amplification. And if you do it in the right way, I will show you that it's possible to have a system that if you inject a photon in the input port, is going to go into the system, propagate unidirectionally, be amplified along the way, and then the whole signal will come out at the output port of your amplifier. And on the other end, if there is some noise, coming from the external world that enters the output port, it has to propagate in the same direction. In our system, it will not be amplified because there will be no phase matching. And then most importantly, we can basically extract it at a sink before it reaches the input port. And so that's why it's going to be fully non-reciprocal. And so in a way, we have obtained basically a circulator, an amplifying circulator, where signal can go from the input port to the output port and be amplified, whereas from the output port, it will be dumped into a sink. Okay, now I wanted to review very quickly the physics of our building block, a parametric amplifier. Here it's also nice that Nicola already did a great job. So I will be very, and probably most of the people are familiar with this anyway, so I will try to be very quick. So basically, the building block of our system is just a single parametric amplifier. You can view it just as a nonlinear oscillator with a natural frequency ω0, and you're driving it at twice, close to twice its natural frequency. And you need an essential ingredient, you need some kind of nonlinearity. And the simplest example of this is just a pendulum that is modulated by changing its length. And it's well known that there are 2 regimes. If you do it gently, basically nothing will happen. And if you do it with an amplitude which is large enough, it will start to oscillate. Funny enough, the parametric amplifier is this seemingly boring situation. Why? Because if I add a signal at the resonant frequency, then it will start to oscillate. And if I compare the amplitude of the oscillation of the one without parametric driving, you see that the amplitude is going to be larger. And in a quantum mechanical setting, I can interpret this by saying that the pump photon are being down converted and split it into a signal photon with half the frequency. All of this is described by the well-known squeezing Hamiltonian, and this Hamiltonian basically describes the exponential accumulation of photon with rate 2 nu, and it's an unstable Hamiltonian, because if there were no dissipation, the photon will accumulate. but I have this like boring situation where nothing happened just because the photons just leak out of my system faster than they are created. Basically, I have a decay rate which is larger than this rate of creation of photon pairs. And if I'm thinking now of an amplifier, the idea is that this decay does not describe dissipation, but it describes the fact that my photon are emitted in the output port. Okay, of course, I can consider this was the situation where I'm driving exactly twice the natural frequency. I can consider a more general situation where I drive close to the natural frequency, and then I have this slightly more complicated Hamiltonian. But if delta, the tuning, is smaller than nu, I can always make a Bogoliubov transformation and have again the Hamiltonian of a resonantly driven amplifier, just with a smaller amplitude of creation. Whereas if the tuning is large enough, I can diagonalize the Hamiltonian again with a Bogoliubov transformation and obtain just a simple harmonic oscillator. Okay, this was the building block, and what we are doing is just slightly more complicated. Now we have many cavity, and we can write the Hamiltonian in the reciprocal space, and there will be a particle conserving term describing the hopping, but we also have a term that describes that we create pairs of photons. And here, so an essential ingredient of our proposal is that the pump photon as a quasi-momentum itself, and so I should have also momentum conservation, not only energy conservation. So the pair that I create, the sum of their momentum is the pump momentum. And basically what we want to have is that once we have diagonalized Hamiltonian and written it in terms of harmonic oscillator and resonantly driven parametric amplifier, we are going to have some unstable mode describing this amplifying normal modes, and we want that this unstable mode is only a topological edge state. So this is the main idea. Okay, here I really have to give credit to people who also had similar idea. In particular, there is this very pioneering paper from Ryan Barnett. This was in a 1D system, so it was at the edge of a 1D system, and he also has a paper in 2D, but our paper together with a paper that appeared at the same time was the first one that showed how to engineer some transport traveling edge state. Okay, and okay, also very quickly, a connection to the talk that it's going to come after mine from Diego Porras. You can view as our system as being governed by a non-Hermitian Hamiltonian. The idea is that if you have parametric term, you can define the number field like you do for superconductor and define an Hermitian Bogoliubov-Degens Hamiltonian. Since they are bosons, when you are diagonalizing your system, you are not diagonalizing the Bogoliubov-Degens Hamiltonian, but rather the Bogoliubov-Degens Hamiltonian multiplied by this sigma Z matrix, and this is a non-Hermitian matrix. For a stable Hamiltonian, everything is very simple. I can just modify my definition of the scalar product, and then I get the same math behind it. For unstable Hamiltonian, like the one of my amplifier, things are more complicated. Okay, here also some advertisement. We had also some paper about the stable regime, where we considered, we have shown that the edge state as so it's propagating robustly, as also some idler part, and also we have a paper with a mathematician describing the bulk boundary correspondence for these bosonic Bogoliubov-Degens Hamiltonians. Okay, now I want to go a little bit more into the details of the system that we came up with. So basically, we consider for the synthetic gauge part the well-known Hofstadter model. So with flux pi half, so the photons, when they go about the plaquette, they will pick up the phase pi half, and we have a square lattice, and we have this pump that you see from this, there is this phase. So the parametric terms are only on site, and there are this phase with a phase. And this describes the quasi-momentum of the pump photons. Okay, so without the parametric term, the band structure look as following. You have rather flat bands, and you have edge states connecting subsequent bands because they are topological bands. And then the idea is very simple. We just want to tune the pump parameter such that we resonantly drive our edge state. For doing this, we just need to enforce momentum and energy conservation. So we drive our pump photon will have twice the momentum of the edge state and twice the energy of the edge state in the middle of the band. And then the nice thing, since the dispersion of the edge state in the region where the dispersion of the edge state is fairly linear, and in the region where the dispersion is linear, we automatically get phase matching. Just with the assumption that and so we get like a finite bandwidth that it's set again by the region where the dispersion is linear. Okay, so until now I'm describing an unstable situation. The question is, how can we stabilize our system? And the idea is that there is a very simple way to do it. So okay, if I don't do it, what happens that any fluctuation that is created will start to circulate and amplify it more and more until my system basically fell apart. And so it's not anymore described by this Hamiltonian. But what I can do, I can just add a waveguide and connect it to a cavity, and in an impeded match way. So since the edge state is chiral, it turns out that just by setting the strength of the coupling, I can tune it at a point where everything that there is no reflection. And this means that the transmission is perfect, is going to be one, because I have just one channel where I can transmit. And so what happens is that if I inject something, it's amplified, it makes a full round trip, but then it's ejected. And so like this, I have arrived to a stable situation, but not yet an amplifier. And then the idea is just to have an amplifier, just to add 3 such waveguides. And then these are really like result of simulation. I plot the amplitude of the wave as a function of the driving phase, and you get this ellipsis. So it's a phase sensitive amplifier. And as you see, everything goes out of the output port. Nothing even reaches the sink. And this works equally well with a perfect system, with a clean system, or with a disordered system. So this is the comparison of the two situations. And so here I don't have any trade-off between gain and bandwidth. The bandwidth is just set by the region where my edge state is linear, and the gain is just set by the length of the amplifier. So I can do the amplifier as long as I want, and I will always increase the gain. And also it's I want to show that it's quantum limited. The idea is that in this case I have a phase sensitive amplifier. So the standard quantum limit is very simple. I will just amplify the signal as much as the 0-point fluctuation. And so if I divide by the gain and subtract the 0-point fluctuation, I get what I add, and this add can be as small as 0. And in my case, I get the added noise can be as small as 0 and in unit of a quantum of noise. And you see here I have very small, and it's robust. So if I have two curves, if I add disorder, I get the same result. And so what is also very nice of an active device is that you can even claim that you have some type of protection against internal loss. This is also a point that Nicola has explained very well. So if you take care to do a good and clean job at the beginning of your amplification stage, so if you are going to have noise here at the beginning, it's bad. So this no topology will help you. But if you're doing a good job at the beginning, if you have some more noise later on where the scenery has been already amplified at a classically accessible level, it doesn't matter anymore. Okay. And yeah, and then here I want to show also that it's fully non-reciprocal. So if you inject something at the output, it's going to be ejected at the sink. And so as a consequence, there is very little back reflection and very little reverse gain. And also, this is also something that has been mentioned by Nicholas. If you have a phase-sensitive amplifier, one quadrature is amplifier and the other is de-amplified, and this leads also to squeezing of fluctuation. And so you can, in principle, use this as a Brown band squeezing generator. Okay, and then another point. So normally if you have a photonic system and it's cold and you don't have parametric term, the steady state is really boring. So you don't have any photons in your system. So then you have a very interesting linear response, but the steady state is just completely boring. Whereas in our system, since we have this parametric term, so one is going to see the presence of non-trivial topology even in the steady states, and you can visualize it by plotting the Wigner function of each cavity. If it's in the ground state, it's just a circle, but it can be squeezed by the parametric term, and it can have a larger area if it's not a pure state. And so this phenomenon is known as quantum eating. So we don't have any thermal excitation entering in our amplifier. We assume that we are at 0 temperature, but still there is some added noise. Okay, do I have 5 minutes more?
Yes, 5 minutes starting from now, yeah.
Okay, so I think I've been very
perfect timing.
Too fast. I fear I didn't have enough time. But okay, so now I come to the potential implementations.
We don't see your full screen, Vittorio.
Sorry.
No, it's fine, yes.
Okay, yeah. So basically there are, I think, 2 most promising implementations. So one is based on this system from the group of Simon and Schuster in Chicago, where they have array of 3D cavities with ferrite sphere in it. And in this system, they have already realized this the Hamiltonian without parametric driving, exactly the one that we have considered of the Hofstadter model with flux pi half. And one can add Josephson junction to add the parametric driving. By the way, so in my talk, I was always, since I'm a theoretician, I was always considering the more elegant situation that where the driving, the parametric driving is everywhere. But actually, this thing would work also if you add the driving only at the edges, which would make the realization technically simpler. And then, okay, this was one implementation, and the other one, which is also pretty close to what we have proposed, is the one that Mittal et al., so from Aphesi group, have used to generate entangled photon pairs. And here you have array of microrings resonator, and it's with silicon, and so it has 4-wave mixing, and this could be used to create a phase insensitive amplifier. And actually, even the system that they have in the lab could be operated in this way. Okay, so I wrap up my conclusion. So I told you about our paper from 2016 in Physical Review X. So we have also a patent, by the way, on it. And I think we can make the claim that historically was the first proposal of a 2D active topological device. And there is interesting new physics that does not have any electronic analog. So in this sense, it could be also could be seen as some precursor of all this interesting work that came up later about non-emission topological physics. And it was also one of the first work that was combining quantum and topological photonics. So with this, I thank you for your attention, and I'm looking forward for questions.
Thank you very much, Vittorio, for the very nice talk. So the stage is open for question. I encourage the attendees to raise their hands so they can pose the question to the speaker themselves. We have some questions already in the chat. So Anya Mettelman asked that if you have lattice of cavities, is your bandwidth set by the line width of these cavities? She also said, okay, answers. So during the talk, maybe you already specified this, but maybe you want to comment.
Yeah, kind of. So I mean, when you mean by bandwidth, yes. So you're thinking that the photons are leaking out of the cavity and go to the next cavity, and then this is like the hopping rate. Yeah, this definitely limits the bandwidth. Is going to be slightly smaller than the hopping rate, because actually the bandwidth is the region where your edge state is going to be linear, and this is going to be smaller than the bandwidth of the cavities. So one nice part of our work, or difficult part, was like to think which, if there are many topological band structure, which topological band structure will have very nice edge state that occupy most of the bandwidth and that they are pretty linear, and that's how we came up with this Hofstadt model.
Okay, thank you, Vittorio. We have another question from Nicola Roth, so I can read it. My probably too naive understanding of your calculations is that you don't take into account self-phase modulation and cross-phase modulation, nonlinear phase mismatches. Is that correct? If yes, why do you perform such approximation?
Okay, so I think I apologize, but yeah, so I do not understand but maybe I can say what we do exactly, and then
I'm trying to unmute Nicola. So.
Maybe I can ask the question directly if it's unclear.
Yeah, it's better. Yes.
So I think at one point you showed us the Hamiltonian, Vittorio. Can you come back? Maybe discuss.
So it's about the linearization of the Hamiltonian, and that
I guess so. Yeah. So it was a
no, that's true. I mean, our was a completely theoretical proposal, so we do not have in mind any specific setup. So at the end, in the outline, we talk about.
So yeah, a bit below. Yeah. I think. Yeah, slightly later.
Sorry. Yes. Sorry. Yeah.
Yeah, it was already. Yeah, this one. So basically, the last term, if I am correct, is the so-called squeezing Hamiltonian, right?
Yeah, that's right. Yes.
Coefficient, and I fear that this new might be K dependent or J dependent in a real circuit. This is what we call cross-phase or self-phase modulation. So basically, this nonlinear interaction depends if it's
I understand what you're saying.
Or the cross terms. I mean, the same indexes or the
I mean, the question is, I understand what you're saying. Yeah, of course, this will depend on the setup, but I want to point out that when we then diagonalize the Hamiltonian, we have this effect, because then the band structure that we obtain will have so it's gone. So I guess that the fact that you have like nu that depend on K has a similar effect as the fact that the slope of the edge state is not linear, right?
And so there are two parts. So I agree with you. If as you showed clearly, you have the dispersion relation, which is linear or not, depending on which state you choose or not. And I agree with you. The more linear, the better. But there is also a nonlinear component in that. So basically, photon number dependent part. Because
okay, yeah, this I
in
agree,
other
yes,
words,
yes.
the linear dispersion relation, I mean the zero power dispersion relation is not the same, might be distorted whenever you pump.
Yeah, sure.
So that's
I mean,
my point.
Yeah, that's true. I mean, of course, this, yeah, we are linearizing an Hamiltonian, and this, yeah, depending on what is the implementation, it will have a limit. You cannot have just infinite gain and hope that the same linearized Hamiltonian will apply. So because you're assuming that there are some more small fluctuation about some, about some classical state. And yeah, so I agree with your point. Yeah, so the answer to this is that since it's theory work and we do not focus on any specific implementation, we didn't describe this. Yeah.
Okay, thanks.
Yeah.
Great. So maybe we have time for one more question. We have still a couple of minutes. So I have a curiosity myself, Vittorio. In your proposal, you mentioned three-way mixing amplification, right? Is this it could be also four-way mixing, or it is specific of this?
Yeah. So for four-way mixing, it would be more natural to have a phase-insensitive amplifier. And indeed, yeah, this is something that I mentioned too quickly at the end. So in this setup that Afesi et al. Have built, they have four-wave mixing. So it's silicon, and so they have a Chi3 nonlinearity, and then basically each photon creates a signal and either photon with different frequency. And then, you could use the signal photon as.
But your proposal can be generalized also.
Can be generalized, yes, right. We didn't describe it explicitly in the paper, but I think we mentioned it in the outlook. But,
And by curiosity, how many unit cells, how many cavities you have in this implementation?
Well, so you can see it from the picture now. I don't know,
okay.
but something like. I mean, the idea is that all this topology business works if you kill tunneling. So in principle, you could have that an edge state is backscattering by tunneling to the next edge. And in particular, for this Hofstadter butterfly model, the edge states are very strongly confined. And so it's enough to have quite a small system. So we could have a much smaller system than this. It was just to illustrate that we can have super high gain.
Maybe experimental is less challenging to
one could
smaller
with less cavities. And I think what is also important, the parametric amplification could be only at the edges, as it is done for these topological lasers. So they don't have gain everywhere; they have gain only at the edges.
Okay, thanks. I think time is over. So thank you again for the nice talk. We can move on to the next speaker of the session. So we have Diego Porras, one of the organizers of the conference from the Institute of Fundamental Physics in Madrid, Spain. So Diego, you can share your presentation. We see it.
Okay.
Yeah, great.
Thank you. You can see the screen, right? Okay, well, I will start by also thanking the other organizers for letting me present in this work. This is the work I'm going to present is theoretical work that we are doing here in Madrid. And there are several people involved, especially two postdocs, Tomás Ramos and Álvaro Gómez León, and other more senior people. And before I start my talk, I would like to, obviously, I don't need to introduce the idea of photonic lattice here. I would just like to remind you that by photonic lattice, we normally understand, we can understand several systems. Some of them are more classical, others are more quantum. And normally, the same phenomenology that we find in photonic systems, we can also find it in optomechanical systems and Byronic lattices as well. Like, for example, in trapped ions, a field I'm very familiar with, you always find the same kind of lattice model, bosonic lattice models that show the very similar phenomenology as in photonic lattices. So basically, I would like just to remind that the physics that we are going to discuss here are kind of, they apply to a collection of systems, although a set of coupled arrays cavities, photonic cavities is kind of the paradigmatic model. These ideas can be extended a bit beyond. So let me introduce my idea by introducing non-reciprocal systems. So basically in this talk, what I will try to convince you that we have developed a theory that, or a theoretical framework that allows us to understand topological properties of basically non-reciprocal systems. So what is the motivation for this? Basically, well, the way I understand a non-reciprocal system is a system where you have kind of a competition or a interference, if you want to understand it like this, between two effects. One is a complex photon hopping between sites, and another is dissipative or collective coupling between different sites. This idea was actually very nicely introduced by Anya in her talk, and they presented this idea a few years ago already. And in the extreme case, when you have this competition between complex tunnelings and dissipative couplings, you can even have systems where propagation is only allowed, or systems are only coupled in one single direction. So if we consider a photonic chain that has these non-reciprocal couplings, we would find a situation where one of the sides receives inputs only from another side on the left or on the right. This could also lead to the effect of directional amplification. By this, I mean that there could be amplification, for example, of a coherent signal in a single direction. So directional amplification is a phenomenon that is, I would say, well understood in a sense. So, and somehow it has some properties that in common with topological systems. In particular, you can easily understand that directional amplification, the effect of directional amplification depends strongly on boundary conditions. If you have periodic boundary conditions, then you would find that a coherent signal would amplify forever. And actually, we would expect that a system that acts as a directional amplifier should be unstable if you consider periodic boundary conditions. The physics of these systems change a lot if you consider open boundary conditions, because here you have a limit to the propagation and amplification effect. And you would expect that there is some accumulation of photonic density in one end of the chain. If you consider a one-dimensional chain with open boundary conditions, you could believe that under some conditions, this is going to be an unstable system. So, and also this accumulation of photonic chains resembles a little bit the spatial profile of an edge state. So the question is there a relation between directional amplification and topology, at least topology as we understand it in the physics of topological insulators? To answer this question, we could just try to formalize the question and study the directional amplification in terms of coupled equations for the amplitudes. And this would lead to basically writing equations of motion that depend on a non-Hermitian coupling matrix. So here we would have to apply the physics of non-Hermitian, topological non-Hermitian systems. from which there is a vast literature right now. But I would say there are some issues to relate the specific questions that we are asking for here, particularly what are the consequences for physical observables in this directional amplification. They are not always easy to address with this non-Hermitian framework. So in order to address this question of how to understand topological properties of these systems, what I'm going to do here is to try to make a connection with the way they address these questions in solid state physics. If we look at electronic systems, the way topological insulators are presented normally, or the way we understand their behavior, is by looking at response functions of these systems. For example, a topological insulator is a system that conducts electricity by means of edge states. So the definition of topological insulator has a physical motivation. It's not a property of, well, of course, it's a formal property of the Hamiltonian that defines the topological insulator, but this property is related to observable, and in particular, is related to the electrical current that is conducted by this system. So we would like to trace a bit of an analogy with photonic systems by investigating topological properties, or by investigating how topological properties affect the response of the system to an input signal. In the case of topological photonic systems, we don't have electric currents, but we have kind of the analogous of electrical conductivity, which is the input-output relations between an input field and an output field. So this approach is what I'm going to call topological amplification, as Vittorio Piano very nicely introduced in his previous talk. Is somehow something that was introduced for the first time in his work in 2016. And we have built on this idea to try to construct a mathematical formalism that allows to describe this input-output theory in terms of topological invariance. This is what was presented in these 2019 and 2021 papers. And the ideas I'm going to present are also strongly related to the work by Van Jura and in Nunenkamp's group, who have also worked on similar lines. So I think all these works here are strongly correlated somehow, and they are all in the they all follow the same spirit of understanding topological properties by looking at response functions in the input-output sense. So basically, the work I'm going to present relies on a formal mapping between non-Hermitian matrices and chiral Hamiltonians. This is somehow the main theoretical idea behind this work. And I'm going to show that by using this formalism, you can show that there is a formal relation between directional amplification and non-trivial topological phases defined in terms of a winding number. And finally, I would like to stress that here we are going to look at a system. We are going to look at a theory that allows us to deal with quantum fluctuations as well, which sometimes is not the case in the description of non-Hermitian topological systems. So let me introduce my idea with a kind of a simple model. This is, I'm going to consider a chain of cavities, and these cavities are going to be coupled by both coherent couplings that have the form of photon tunneling couplings. And I'm going to add some collective dissipative coupling between these cavities. This model is basically a generalization of the model that Anja Nettelmann presented yesterday. It's just the generalization to many sites. And it's also known in the literature as Hatano-Nelson model. If you want, this is the kind of the simplest model for a many-site directional amplifier. So what's so special about this model? I'm going to consider, as you see, I'm considering here both coherent couplings that have the form of photon tunneling. This is this TC. And I'm going to consider as well that these tunnelings can have a complex phase, this phi. This is obviously not always easy to achieve in an experiment. There are several possible implementations of these complex tunnelings. The one that is very promising is considering Fock engineering. There are also other proposals that rely on circulators and magnetic fields. And concerning the dissipative coupling, this is also a highly non-trivial term. And there are also several ways in which you can have a dissipative coupling between cavities. And one of them is, of course, by using an auxiliary dissipative system that acts as an intermediate system to connect to cavities. This is also basically the reservoir engineering idea that Daniel presented yesterday. And also there are some situations where cavities are actually coupled by evanescence waves, and they sometimes can be described in an effective way by a dissipative coupling of this form. So if I apply the input-output theory from textbooks to these systems, what I find is that field operators at each cavity are going to be, the dynamics of these operators are going to depend, of course, on these coherent couplings and dissipative couplings as well. You can see that because of the Heisenberg equations, it's easy to understand that these dissipative and coherent couplings, they come with different phases into these equations. And in the input-output formalism, I have to add up some Langevin forces or operators that are responsible for noise. So probably many of you or all of you are familiar with this input-output relation. Probably the most intuitive part of this equation is the operator part. But in any case, there are situations where this can be even simplified. For example, if I have this phase exactly pi halves, then we are in this regime of full reciprocity where coupling is totally suppressed in one of the directions, and you keep only a real coupling between sites j and j-1, for example. This is the regime of directional amplification, and that's actually not very difficult to understand, basically because you can easily see that any input in cavity j-1 is going to get amplified to cavity j. And well, of course, this can be extended to basically any geometry. And whenever we consider more complex systems, we will find that we will consider different couplings with different dimensionality, but the structure of the problem is always the same. So how do we solve this problem? Basically, in input-output theory, what we would do is to go to Fourier space, go to the, instead of working in time, we would prefer to work in frequencies. And the solution to the expression for operators in terms of input fields is going to depend on the inverse of the coupling matrix. So we have this sort of green function Q that is the inverse of H plus I omega. This formalism allows me to calculate everything. I can calculate the gain, which is going to be given in terms of this green function Q, and I can also calculate noise. And if you look at the expression for noise, it has a very intuitive expression in terms of this propagation matrix Q or green function. And basically, this expression for the noise is telling me that the incoherent contribution to the number of photons is going to depend on the propagation of incoherently emitted photons. This gamma P here is the incoherent couplings in the system, and noise is going to depend on that rate of incoherent emission of incoherent photons amplified by this Q matrix. Okay, this is nice. So far this is a textbook input-output theory applied to this chain, and now you could take all this and just make numerics and predict everything in this system. But where is topology here? Again, let me stress that we have seen here that we have this directional amplification, time reversal invariance is broken. So everything points out to the very similar physical concepts that we find in topological insulator theory, but there is no obvious reason why there is a topological invariant here or anything that can be understood in a topological framework. So here is where the main idea of the foundation for our theory comes about. So let us think again about what we are doing. We have our output fields, or the cavity fields, sorry, as a function of input fields, and they depend on the inverse of the Hamiltonian. Now, if you have ever worked with non-Hermitian matrices, you may have found that they are quite nasty. So you find all kinds of problems when you diagonalize them, and also you don't have an orthonormal basis of eigenvectors. So for a theory, they are a bit like a nightmare. So something that you can do is to work with something else that is called singular value decomposition. So this is very, very used in quantum information theory, not so much in quantum optics. But basically here what we would do is to take our Hamiltonian matrix, if you let me, or my coupling matrix, and express it as in terms of two unitary matrices, U and V, and a matrix of singular values. So this is kind of a similar thing to diagonalization, but it's more general than Hermitian matrices. Now, if I have this singular value decomposition, I can calculate Q, and my green function is going to depend on the singular values and singular vectors. That's also a mathematical trivial identity. Now, there is a funny thing about the singular value decomposition, because it turns out that the singular value decomposition is equivalent to the diagonalization of an effective Hamiltonian H. And this is somehow a very useful observation, because now, if we work with the singular value decomposition, then we can make a description in terms of effective Hamiltonians. We don't have to work with non-Hermitian matrices. We can work with eigenstates of this enlarged Hamiltonian H. And what is nice about H is that it has exactly the same form that Hamiltonians in topological insulator theory. It has something that is called chiral symmetry in topological insulators, which is basically this block structure with two zeros in the diagonal and this HH dagger in the non-diagonal. So most Hamiltonians in topological insulator theory, Hamiltonians like for the SSH model and other more complex models, have this structure, and they have H states. So what happens if this guy has an H state? Well, if there is a zero energy H state of H, this means that there is a zero singular value. But remember that the green function depends on the inverse of the singular value. So if there are H states of H, there are singular values on Q, and this leads to exponential amplification of the response function of green function Q. So this is basically the basic idea over which one can build now a topological theory of directional amplification. Basically, whenever you have a non-Hermitian coupling matrix, you have to build your effective Hamiltonian, and you can be sure that amplification is going to be given by the zero energy states of this enlarged Hamiltonian. And this means also that zero singular values are going to be related to zero eigenstates of the effective Hamiltonian, and H states of the effective Hamiltonian are going to shape the way directional amplification works spatially. So the profile of directional amplification, of exponential amplification, is actually an H state of this enlarged Hamiltonian. So this is where we find this link between topological insulators and photonic lattices. Now, if we put this to work, we just have to focus again on a particular example. And again, I'm going to talk about this Hatano-Nelson model, although we have some work in progress about how to apply this, for example, to coupled parametric oscillators, parametric amplifiers, sorry. But maybe the simplest way to illustrate this idea is by looking at again at this Hatano-Nelson model. So if I use this model, then I can just build my effective Hamiltonian, and it turns out that this effective Hamiltonian is exactly the one for the SSH model. So this allows me to bring all the physics from topological insulators, in particular for SSH models, and use it to predict or to analytically calculate the Green function determining the input-output relations in this particular example. And this allows me also to predict under what conditions this system is going to behave as an insulator, and calculate also the exponent for amplification, which is actually related to the exponent of the edge state of the SSH model. Sorry, and there is also another result about the bandwidth of the gain, which can be also predicted with this formalism, and it turns out to depend basically on the coupling parameters and to decrease with system size. You can also use this formalism to calculate noise in the system. Remember that this input-output formalism is a quantum formalism, so we can calculate now fluctuations as well as mean values of observables. And you can find the details in the paper, but just to summarize what we have found for this particular model is that in the limit of exponential of directional amplification, we find that added noise remains close to the quantum limit. We find values of 1, whereas the added noise is limited by 1/2, so it cannot be better than 1/2. So basically what we find is that, at least theoretically, this model predicts exponential gain, while added noise is still under control and close to the quantum limit. So let me just finish this talk by some work in progress. So basically, what is very appealing for a theorist, and I think from a fundamental point of view, is that we have found a theoretical description of topological properties where the effective matrix that we built depends on the frequency of the system, or basically on the frequency of the photons involved in the amplification process. So this is true both for the amplification of a coherent signal as well as for the noise in the system. So to say, each frequency has its own topological index in this problem. So in a sense, it looks like if the problem is factorized in different frequencies. So this is an idea that intuitively is clear from the input-output formalism, which is solved in frequency space. And we have formalized it by trying to make explicit this description of the system as a product of systems with different photonic degrees of freedom with different frequencies. And the ideal framework for this is Keldysh theory, where you can calculate correlation functions in terms of a generating functional that plays the role of a density matrix operator, in a sense. It's not exactly that, but it has many of its properties. So by using this formalism, we can calculate Green functions by taking derivatives of this generating functional. And because each generating functional has its own winding number, what we find through the Keldysh formalism is that we can make a topological classification of phases that applies to Green functions as well, not only to the usual photonic spectral densities, but it applies to more generally to any response function in the system. And in this formalism, all these Green functions, they have a similar description in terms of the inverse of an effective Hamiltonian. So we can extend our formalism to predict properties and to describe the Keldysh generating functional in terms of a winding number that depends on the frequency. So these are the conclusions. I think the chairman is already showing me that there is little time left. So let me just say that we have presented a theory that links directional amplification and topological insulator theory, and also gives a definition of what does it mean to have a topological dissipative phase transition in a dissipative system. And some of the outlook that we are considering is applying these ideas to a concrete setup for single photon detection, or something that is that takes into account the experimental details of the problem. And just let me finish by thanking my collaborators, in particular Tomás Ramos and Álvaro Gómez León, who are postdocs in our group, and also the senior people here, in particular Alejandro González Tudela, who is also an organizer of the conference, and Juan José García Ripoll. And thank you for your attention.
Thank you very much, Diego, for the very nice talk. Thanks a lot. So the stage is open for questions. I see one raised hand. I will give priority to raised hands. So there is Nicola. I think I unmuted you. Let's see. Yeah.
Actually, I was clapping, but I can.
You were clapping. Well. Sorry. sorry.
So actually,
sorry.
I had a question, but thank you.
Okay, so if you want to go ahead.
Diego.
Yeah.
Yeah, it's a very naive experimentalist question. Would you have any simple explanation why does your amplifier, I mean, at least the scheme you looked at, does not reach the quantum limit? Is there some physical explanation, or is it just a matter of fine-tuning the parameters?
Well, to be honest, I don't have an intuitive explanation why I don't get to have one half. I have to say the model that we have studied is this Hatano-Nelson model, which is, I would like to look at other models. Like, for example, we know that the same theory or the same thesis also can be applied to, so the same formalism can be applied to a system of coupled parametric amplifiers, where you have a little bit of some different elements in the theory, because you have to extend this formalism to include Bogoliubov, the Bogoliubov formalism, and so on. But basically, the same ideas apply. And I would be curious to see whether there you can find the true quantum limit for added noise. But here, it's just a result of the calculation. I would like to have an intuitive explanation, but the truth is that we don't have it yet.
Thank you, Diego. So there is a question from the chat from Anya Mettelman. In your driven dissipative dynamics, if the dissipative coupling induces anti-damping, shouldn't you couple to the adjoint operators?
Sorry, can you say it again?
It's in the chat, so if you want to read it as well. In your given dissipative dynamics, if the dissipative coupling induces anti-damping, shouldn't you couple to the adjoint operators?
Well, basically here the dissipative coupling is a pumping term in the model that we have considered. Actually, there are several ways you can implement this model, but in the implementation that we have studied, you have this coupling, which is a D-dagger. It's a sort of, as Anya says, it's anti-damping mechanism. So the way you physically get it by reservoir engineering is by having a sort of squeezing coupling or parametric amplifier coupling with an auxiliary state. So in that sense, you are right, Anya, that if you want to get this dissipative coupling, then you have to couple your cavities with auxiliary systems, and you need to have something of the form A dagger, B dagger, plus AB. And then if you trace out the dissipative the auxiliary system, then you have the coupling that you want. So in a sense, the model that we have studied is kind of a descendant of a parametric amplifier. It's only that the parametric amplifier is hidden in the auxiliary systems that are at the origin of the dissipative coupling.
So can I just ask, like, so if what you're saying, your jump operator in our language, it looks like it has to be something like like say it's A1 and A2, A1 dagger plus A2 dagger to get anti-damping in this form. But you're saying now this would look different?
So if you want to have anti-damping, then yes, you have to. If you want to have anti-damping collective couplings, you need to have A dagger, B dagger, rho, A B. So you need to have this anti-damping collective coupling, as you say. This would be the ideal coupling for this parametric amplifier, because this is giving you at the same time the extra incoherent pumping that you need for the amplification to work, plus collective coupling. There are other combinations that would work as well, but this would be the more efficient one.
Yeah, but if you have this, then you couple to the adjoint operator, the induced coupling. We can talk about this in
Yeah. Okay.
But this will make
it's a very interesting. Yeah, there are many details that you have to take into account, but yeah, we can talk about this later. Thank you.
Thank you, Diego. So maybe we can ask the other question we have in the chat. Lavi, if you want to pose the question yourself, just raise your hand. Here you are. So I try to unmute you. Yeah.
Yeah, hi, thanks. So actually I had a very naive question because I was not very familiar with these aspects. So I hope I'm audible. Yeah. So the question was, usually the topological aspects make sure that the states only propagate in one direction. But on top of that, you had this non-reciprocal aspect. So I was just trying to understand that by adding this non-reciprocal aspect, we make our system non-Hermitian in this fashion. And then with the help of this way of achieving non-hermiticity, we could have like topological amplification, because somehow all the bulk states would also will travel, not only the edge states. So I was just trying to understand if this is what you were trying to understand, just to have a general overview.
Yeah, well, that's a good question. I mean, I understand there are several ideas that can be a bit confusing here, but the main idea of this work is that we are considering systems that are not topological without dissipation. So this is not a theory for a system that is topological because you have a photonic lattice that has whose Hamiltonian is topological. This is a system where the systems we consider here are systems that are not topological, and it's only the action of both coherent coupling and dissipation that makes them topological. So basically, this in our theory, topology emerges directly from non-reciprocity, which is it's not like we have a topological system and then we have non-reciprocity. We have a trivial system, and then you add dissipation, and then you get a topological system.
So it's like a non-dissipative driven topology. So
that's right, exactly that. So it's theory that is related only to non-reciprocity. That's the only element that you need.
Okay, thanks.
Thank you, Diego. So maybe since we are at the end of the session, I will ask a question myself. So how do we understand the phase matching in this framework? In parametric amplification, we need to have a phase matching condition as well.
That's a good question. I think so. From our theory, what we find in the end conditions for that allows us to predict when a system is going to behave as a directional amplifier or not. This condition is basically that there has to be. This depends on the model. But if you go to this Hatano-Nelson model, for example, here you have. The condition is that the winding number has to be different than 0. And this, if you use the theory, this leads to This allows you to calculate this edge state, spatial dependence, and basically everything. Now, this is all defined in a lattice, in a discrete system, but obviously, I think that if you go to the continuum, it probably under some, and if you extend this theory to couple parametric amplifiers, then there has to be a way to reproduce phase matching conditions from the winding number condition. This is just something that we don't know how to do yet, but I think there has to be if you take the continuum limit appropriately, then you have to find that the two things are the same, basically, that both directional amplification,
they can be mapped into each other.
Yeah, there has to be a way to rewrite these conditions.
Okay, thank you very much, Diego. We are a little bit over time, but I hope it's fine. So let's thank again virtually all the speakers of the sessions. It was very interesting. So I think there is a break now, and maybe,
yes, I wanted to make just a small announcement. I think now during the break, the NASC organization will open the breakout rooms, but they will, it will be open in the same link, no? David, correct me if I'm wrong. It will be, you can come here and
yes,
you're right. There will be the breakout rooms, and just to say that imagine that all the posters will be presented during the 2 days. Imagine that you want to go out of your poster, no? If you are a presenter because you are interested in other. So the breakout room will not close. It will just be empty. So if somebody enters, nobody will be there. But so you can afterwards come back and no, start sharing again. No.